Well, let us see some of the standard formula for the self-inductance and mutual inductance. Now, the self-inductance, if you see for a plain coil, the self-inductance value L is equal to mu 0 times pi n square R upon 2, where n is the number of turns in the coil, R is the radius of the coil, and mu 0 is the magnetic permeability of vacuum. In the same way, the self-inductance of a solenoid, as we have seen, is mu 0 times n square capital A upon L, where capital A is the area of the solenoid, cross-sectional area of the solenoid, and n is the number of turns and small l being the length of the solenoid. Solid cylindrical conductor. For that, the self-inductance L will be equal to mu 0 times small l upon 8 pi, where small l is the length of the solid cylindrical conductor. And again, if you see to the self-inductance of two parallel wire carrying current in opposite directions, which is also known as lead and return wire, because current in one is leading and in another it is returning. For that, the self-inductance is L is equal to mu 0 times small l upon 8 into ln, means natural logarithm times of d minus a by a, where d is the separation between these two wires and a being the cross-sectional area of each of the wire. Now, in the same way, the coaxial hollow cylinder, for that the self-inductance is mu 0 times small l upon 2 pi times ln b by a, where a and b are the respective radius, interior radius of the cylinders, hollow cylinders. One is the internal radius and b is the external radius, and L being the length of the coaxial hollow cylinders. Similarly, if you see to the coaxial solid cylinder, in that case the length, the self-inductance is within bracket mu 0 times small l upon 2 pi times ln b by a plus, as usual, mu 0 by 8 pi. Now, if you see to the toroidal coil with a rectangular cross section, for that the self-inductance is mu 0 times n square h by 2 pi times ln b by a, where a and b are the respective internal and interior and outer radius of the solenoids, and n is the number of turns, h being the width of toroidal solenoid. In the same way, the toroidal coil with circular cross section, if you see, so you have to replace in the formula, that is mu 0 times n square a by 2 pi r. In the same way, if you see to the mutual inductance, two coaxial solenoids, in that case the mutual inductance M, which is equal to mu 0 times n1 n2 times capital A by small l, where capital A is the area, cross-sectional area of inner solenoids, n1 n2 are the number of turns in each of the solenoids, and small l is length of larger solenoid. If you have two coils with a different radius, one is bigger and another is smaller, the number of turns here we take is n1, and r1 is the radius which is greater than the radius of the second coil, and here the number of turns in the second coil is n2. If we see to the system and they are separated by a distance small d, in that case the mutual inductance between these two coils will be equal to mu 0 pi r1 square r2 square n1 n2 upon 2 times within bracket r1 square plus d square whole into 3 by 2. This is the formula for mutual inductance for these systems, where the R1 radius of this coil is greater than the radius of the second coil. And if you see, if the distance of separation between these two coils are considerably high, means this D is very greater than the radius of R1 as well as R2 obviously, So in that case, the formula reduces to m is equal to mu 0 times pi r1 square, r2 square, capital N1, capital N2 upon 2 d cube. That is the formula when the separation is too large. And if you see in the same way, the d, which is the separation between these two coils, equal to 0. That means they are in such a system where they are coaxials in both of the center merging together. In that case, the formula reduces to mu 0 times n1 n2 pi r2 square by twice r1. This is the formula for a two coil system at different separations. Now if you see, when the R1 and R2 are same, that means these replaced with the same radius, that means the radius of these two coils now R1 R2 is equal to same, then the mutual and the number of turns are also N1 equal to N2, then the formula reduces to mu 0 times pi n square r to the power 4th divided by r square plus d square whole to the power 3 by 2, where r is the radius of each of the coil and n is the number of turns each of the coils and d is the separation of these two coils. So in that case, this is the formula how you can calculate the mutual reductance. These are some of the formulas which are helpful in estimating the values in standard problems.